Hey everyone, welcome back to our channel. Today, we've got some exhilarating space news. The James Webb Space Telescope has just captured the first real image of 3I/Atlas, the first confirmed interstellar comet. In this video, we'll break down what makes this discovery so important, how Webb managed this feat, what it tells us about the comet, and what lies ahead in interstellar exploration. Stick around, you're going to want to see this. 3I Atlas is a comet that doesn't originate from our solar system. That's what interstellar means. It is passing through from deep space. Prior to its discovery, we had examples like Oumuamua and 3I Borisov, but each had ambiguous traits. 3I Atlas brings a fresh opportunity, a cometary body with volatile materials, dust coma, tail structure, things we can analyze in depth. Scientists had predicted it would provide new insights into how comets form in other star systems, and now it has. It offers a chance to compare building blocks from far beyond our neighborhood with those in our own solar system. The James Webb Space Telescope, JWST, is uniquely suited for this kind of mission. It operates in infrared, giving it power to see faint objects and differentiate features in dust and gas that are invisible in optical light. Webb's instruments focused on capturing the thermal emission and reflected sunlight from the comet's nucleus and coma. The telescope's stability, sensitivity, and location beyond Earth's atmosphere at L2 point gave it a clear, unobstructed view. The resulting image shows fine structure, the dust environment, and possible jets or outgassing regions, data that ground-based telescopes would struggle to resolve. From the image and supporting spectral observations, scientists can infer the composition and activity of 3I Atlas. The data suggests the presence of dust grains, possibly ice sublimation, and some gas species. By analyzing brightness in different wavelengths, they can estimate the size of dust particles and gas-to-dust ratio. The detection of jets or asymmetries in the coma signals how active the nucleus is. This is huge. We can, for the first time, witness the behavior of an interstellar comet in detail, how hot it gets, how volatile materials evaporate, and how the solar wind shapes its tail. These insights help unlock secrets of comet formation in other systems. This real image is not just a photo, it's a major milestone. It bridges observation and theory. We now have empirical evidence to test our models of comet formation in alien star systems. It challenges or confirms ideas about the distribution of ices and dust in protoplanetary disks elsewhere. Also, studying an interstellar visitor gives context to how common or rare certain elements and chemicals are in galactic space. It opens doors to learning about galactic mixing, the exchange of material between star systems, and the building blocks of planets and life. In cosmochemistry, connecting local samples to interstellar ones is a huge leap forward. Now that we've got this first solid image, follow-up missions and observations will be crucial. Ground-based telescopes, space telescopes across wavelengths, and possibly even mission proposals might try to intercept or sample such objects. Scientists will track 3I Atlas's trajectory, monitor changes in activity as it approaches and recedes from the Sun, and compare observations over time. Future interstellar objects might be discovered earlier, giving us more warning and time to plan. Webb and its successors, like OST or LUVOIR, can repeat this feat. The era of interstellar comet science is just beginning. Scientists are computing the precise trajectory of 3I Atlas as it travels through our solar system and then back out into interstellar space. By measuring small perturbations, gravitational influences of planets, and non-gravitational forces like outgassing, they refine orbital models. The data helps predict where the comet will be visible, how bright it may become, and when to schedule telescope time. Detailed orbit tracking also tells us whether it came from a particular direction or region in the galaxy, offering clues about its home system. With Oumuamua and 2I Borisov as precedents, astronomers compare their known features, shape, activity, composition, with 3I Atlas. Oumuamua was mysterious, showing non-gravitational acceleration but little gas emission. 2I Borisov more comet-like. 3I Atlas slots somewhere in that spectrum. By comparing brightness curves, dust production, and spectral lines across all three, researchers can spot patterns or anomalies. This comparative framework helps understand whether 3I Atlas is typical or exceptional. Beyond imaging, spectroscopy is key. Webb and other spectrometers analyze how 3I Atlas absorbs and emits light at distinct wavelengths. That lets scientists detect molecules like water, carbon monoxide, carbon dioxide, and organic compounds. These chemical fingerprints give insight into what ices or volatiles the comet is composed of. Differences from solar system comets could indicate variations in stellar environments, protoplanetary disk chemistry, or even interstellar processing over eons. The light scattering and thermal emission tell us about dust grain sizes and distributions in the comet's coma and tail. Webb's infrared sensitivity helps detect smaller, cooler grains that optical telescopes might miss. Understanding grain size helps model how dust moves, how sunlight pushes it, radiation pressure, and how it contributes to the comet's brightness. If the size distribution differs from solar system comets, it may hint at different formation or evolution histories. Images sometimes reveal jets, localized, strong emissions of gas and dust from active regions on the nucleus. Tracking when and where these jets form and how they vary helps map the nucleus's surface, rotation, and thermal behavior. In 3I Atlas, detecting distinct jets provides clues about internal heat, volatile reservoirs, and how the comet responds to solar heating. Patterns of activity over time also reveal seasonal or rotational effects. Understanding the rotation rate and axis is crucial. Analysis of periodic brightness variations, combined with resolved imaging, can allow estimation of the nucleus shape and spin state. Is it tumbling? Does it rotate uniformly? These dynamics influence how the comet's surface heats, how jets develop, and the long-term stability of activity. Comparing the spin of 3I Atlas with solar system comets tells us whether interstellar objects behave similarly. As the comet approaches the sun, solar heating causes sublimation of ices. Thermal modeling predicts how heat propagates into the nucleus, how deep volatile layers may lie, and how the structure reacts. Observing how the comet's ion tail forms and behaves helps characterize the particle environment and electromagnetic interactions. Any deviations from typical comet solar wind interactions may reveal interstellar histories or unique features. Astronomers produce brightness forecasts to tell observers when and how well 3I/Atlas can be seen from Earth or space telescopes. These predictions factor in distance, phase angle, sun-comet observer geometry, dust production, and gas emission. If the comet brightens more than expected, amateur astronomers might capture it. Coordinated observation campaigns across radio, optical, infrared are scheduled based on these forecasts to maximize science return. From space telescopes like Webb, Hubble, and others to ground observatories across continents, scientists plan coordination. Radio telescopes, optical networks, spectroscopic arrays all point to 3I Atlas simultaneously. By pooling data, they can cross-validate findings, cover more wavelengths, and fill gaps. Citizen science and amateur contributions may also help monitor brightness changes or morphological evolution. International collaboration is crucial. One tantalizing question: where did 3I/Atlas come from? Using its incoming velocity vector, direction, and motion relative to the galactic frame, scientists attempt to trace backward to possible home systems. The more precise the orbit, the narrower the candidate list of stellar systems. While uncertainties are large, over time this could tie the comet to a known star or region, a direct sample from another system. The properties of 3I/Atlas inform theories of how comets form in protoplanetary disks around other stars. Differences in ice fractions, dust composition, and activation thresholds reflect disk chemistry and planetesimal formation conditions. If interstellar comets follow similar patterns to those in our system, that suggests universality. If not, they force us to revise models about how material is assembled in different stellar environments. Interstellar objects like 3I Atlas represent material exchange across star systems. Over billions of years, ejected comets may wander, some entering other systems. That hints at a seeding process. Comets carrying organic molecules, water ices, or building blocks of life may travel between systems. Observing such a body gives empirical weight to panspermia ideas or galactic mixing models. The success of imaging 3I Atlas teaches instrument engineers lessons: sensitivity requirements, pointing stability, spectral coverage. Future telescopes, e.g. LUVOIR, HABEX, may incorporate designs specifically to catch interstellar objects. The agility to respond quickly will matter. The methods refined here, image processing, tracking faint moving targets, coordinating scheduling, become templates for next generations. This cosmic event is also a way to inspire public interest in astronomy and STEM. Sharing images, simulations, and explanations broadens awareness. Schools, planetariums, media can bring this to people, cultivating passion. 3. iAtlas's story becomes part of our human narrative of exploring the unknown, encouraging future scientists and citizen observers to watch the skies. All observations, images, spectra, and models will be archived in public repositories. Open access ensures any researcher worldwide can examine, test, and build on them. Cross-disciplinary studies, from astrochemistry to planetary science, can tap into the data. Long-term archives let future generations revisit the data with improved methods or new questions. Often in frontier science, surprises emerge: unknown molecules, weird dust features, unexpected jets. 3I Atlas may host phenomena not seen in solar system comets. Scientists will remain alert for anomalies. These surprises may upend assumptions, opening new avenues of theory or experimental design. The unknown is part of the thrill. If 3I Atlas contains organic molecules or precursors, it gives clues about the distribution of life's building blocks beyond our system. Comparing its organic inventory with comets in our solar system may reveal whether such chemistry is universal. That helps assess how common the ingredients for life may be across the galaxy, a key question in astrobiology. Sustaining the momentum will require funding, agency support, and mission proposals. Agencies like NASA, ESA, JWST may fund specialized comet intercept missions, new telescopes, or rapid response observatories. Policymakers need to see value in exploring interstellar bodies. Public and scientific advocacy will help secure resources for the next steps. Scientists are comparing 3I Atlas's dust composition with theoretical cosmic dust models to trace its possible stellar nursery. Each system's dust carries a distinct signature based on the parent star's metallicity and temperature. If the spectral data from 3I Atlas aligns with known dust models from specific galactic regions, it could point to its origin thousands of light years away. This cross-referencing helps refine galactic evolutionary models and enhances our understanding of how material circulates across the Milky Way. The James Webb Telescope's infrared instruments allow mapping of temperature variations throughout the comet's coma. These maps show where gas and dust are densest, how energy flows, and which areas heat or cool fastest. By building 3D thermal maps, scientists can visualize how sunlight drives sublimation and how dust particles are distributed. Such high-resolution mapping was never possible before Webb, marking a new level of detail in cometary science. Recent spectral readings hint that 3I/Atlas may carry complex organics, hydrocarbons, alcohols, or even amino acid precursors. These molecules are fundamental to life as we know it. Detecting them in an object from another star system suggests that organic chemistry is not unique to our solar neighborhood. This could strengthen the hypothesis that the ingredients for life are widespread across the galaxy, possibly making life itself more common than we ever imagined. By measuring ratios of different ices, water, carbon monoxide, methane, and ammonia, scientists can infer the temperature and pressure conditions under which the comet formed. Each ice condenses at a different temperature, leaving a thermochemical fingerprint. 3I Atlas's ice ratios may indicate formation in a colder, more distant region of its home system, possibly beyond its original snowline. This provides crucial insights into how other star systems evolve and distribute material. This plays as 3I Atlas nears the Sun, its surface undergoes rapid change. Layers of ice vaporize, exposing deeper material. Observations across multiple weeks show how erosion reshapes the nucleus. By analyzing these changes, scientists can estimate the strength, density, and porosity of its surface. Erosion studies also help simulate how comets age over time, both in and beyond solar systems. Spectroscopic isotopic ratios, such as deuterium to hydrogen, DH, act as galactic tracers.
3I by Atlas's isotopic values may differ significantly from those of Earth's water or solar system comets, hinting at an entirely different galactic environment. These ratios could confirm whether it originated in an older, metal-poor region or a younger, active star-forming zone. In essence, isotopes tell the story of a comet's birthplace in the cosmos. Before entering our solar system, 3I by Atlas spent millions of years traveling through interstellar space, exposed to cosmic rays and radiation.
This exposure likely altered its outer layers, forming a hardened, carbon-rich crust. By analyzing the differences between its irradiated surface and freshly exposed interior material, scientists can estimate how long it's been traveling and how deep radiation effects penetrate, effectively reading the mileage of the comet. Every interstellar object is like a cosmic time capsule. 3I Atlas carries within it the record of chemical evolution that occurred around another star, perhaps billions of years ago. Studying it helps us understand how matter moves and transforms through time, contributing to the grand story of galactic evolution. It reminds us that the material that makes up our world is part of an ongoing galactic exchange, stardust traveling endlessly through eternity. As technology improves, even small telescopes can track faint objects like 3I Atlas. Amateur astronomers worldwide are contributing data, light curves, timing measurements, and even spectra. This collaboration between professionals and enthusiasts strengthens global science. Projects like NASA's Planet Hunters or Zooniverse show that when people unite for discovery, humanity itself becomes part of the cosmic observation network. Determining the nucleus size of an interstellar comet is tricky. The coma's brightness often hides the solid core. Using Webb's infrared data, scientists subtract the diffuse glow to isolate the core signal. Early estimates suggest a nucleus a few hundred meters wide, but ongoing refinement continues. The more precise the measurement, the better scientists can model its mass, density, and evolution. 3I/Atlas moves at extraordinary speed, tens of kilometers per second, fast enough to escape the sun's gravity permanently. These bodies wander for eons until captured temporarily by another star's gravity. This process connects every solar system, a galactic circulation that unites the cosmos through shared matter. Though intercepting 3I/Atlas is nearly impossible due to its speed, scientists are already planning strategies for the next interstellar comet. Robotic interceptors, fast launch systems, or swarm probes could one day collect dust or gas samples for return to Earth. Such a mission would give humanity the first physical sample of material from another star, a monumental leap for science. Beyond the science, 3I Atlas evokes deep philosophical reflection. We are witnessing matter from another sun, older than our civilization, passing briefly through our skies. It's a reminder that we are part of something vast, interconnected, and ancient. Each interstellar visitor whispers of unknown worlds and cosmic histories, bridging the gap between science and spirituality. Educators worldwide are already integrating 3I Atlas into curricula. Using real data from Webb, students can learn orbital mechanics, spectroscopy, and cosmic chemistry. These discoveries motivate young minds to think beyond Earth, to dream, calculate, and question. The comet becomes a living classroom for the next generation of astronomers and explorers. The successful imaging of 3I Atlas reinforces JWST's place in history as more than a telescope. It's a time machine and cosmic archaeologist. Its ability to detect the faintest interstellar travelers proves that human technology can reach across time and space. Every new discovery builds upon this legacy, ensuring JWST's data will influence astronomy for decades. With 3I Atlas, we're reminded that our solar system is not isolated. It's part of an intricate, living galaxy.